This is one of those important identities for differentiation. As we take the derivative of a function, the natural logarithm of z is equal to a rational expression 1 over z. This was true during the real number system, and this is also true for this complex number system. But of course, we need to show that to be true first before applying that to some examples later on. So here, we're going to have our function be the natural logarithm of z. And we are going to use here the definition for a derivative of a complex function. The definition for this is actually the limit of your function of z plus delta z minus f of z all over your delta z as delta z approaches 0. The goal later is to find the equivalent form of this, as this is already given to be our natural logarithm of z, and at the same time apply some processes that will actually cancel this, because we don't want that to reach 0, making our limit undefined and making a derivative not to exist. So copying our function here, let me have it here on this separate scratch paper here. Our function of z is the natural logarithm of z. In short, if we have here the function of z plus delta z, it would be equivalent to the natural logarithm of z plus delta z, right? Only substituting this on our given, getting that form. Now, if we're going to plug that in here, you would notice this to happen. The limit of your function here, we have here the natural logarithm of your z plus delta z minus the original function natural logarithm of z all over your delta z as delta z approaching 0. We cannot combine this immediately because they are of different compositions. The first one is z plus delta z, and the other one is just z for the natural logarithm. So what needs to be done here so that we could actually remove this later on? Take that we cannot take that out and stating that it's just 1 over delta z and taking that out here, because it's the expression we are going to take the limit at. But what we can actually do here is still taking that out, but not outside the limit. Okay? What we can do here is writing in this manner the limit of you have 1 over delta z, sorry, that's z, as delta z approaches 0, right, times the natural logarithm, natural logarithm of your z plus delta z minus the natural logarithm of your z. Notice this is just a fraction or rational expression, so this is equivalent to this. And if we're going to multiply that, you will return to the previously given or identified expression. Why we're doing this? Because this too has natural logarithms, and therefore they would behave the same way as those rules or properties of logarithm. If we have the difference of the same natural logarithm or natural logarithm on the same base, or logarithm on the same base, we can apply here the quotient property. It will be looking like this. The limit of, again, delta z approaching 0, we still have 1 over delta z here. But what will happen to the remaining item here? By the way, sorry, I need to emphasize that to be true just like this, because it's the product with the difference, right? So this would become the natural logarithm of your z plus delta z over z. Okay, because that is the quotient property of logarithm, as this is still a logarithm in nature, just natural logarithm. So if we're going to write it into different natural logarithms or natural, if we would like to write this in this form, that would be its equivalence. Okay, so what is the purpose for that? The purpose for that is simplifying this further. You will have here the limit, again, delta z approaching 0. I still have 1 over delta z here, and you will have here the natural logarithm of, you have z over z plus delta z over z, right? As you share this denominator to all the terms of your numerator, making this 1. Okay? The reason for that is we have an identity that we may invoke later on. Okay? The limit, you still have here delta z approaching 0, 1 over delta z still, and you will have here the natural logarithm of your 1 plus delta z over z. Okay, now from this perspective now, I would like us to also apply another property of logarithm, calling this now as 1. So take note that if you have a constant here, any value, say for example, it's k logarithm of b, right? This can be written as the logarithm of b to the power of k. That's the power property. Okay? Earlier, it was actually like this, the logarithm of a minus logarithm of b is equivalent to logarithm of a over b as long as b is not equal to 0, right? That's what happened here. Okay, this one here. Okay. Now, we can also use the power property. I would like us to do that because it will be something like this. Okay, this form still. You will now have the natural logarithm of 1 plus your delta z over z to the power of 1 over delta z. Okay, so we are getting closer to our goal, but it's still not there yet, because we would like to really show, because if we're going to use 0 still here, you will still have an exponent which is undefined, and basically everything else will be undefined even if this is already good. What we can do here is to assume some equivalence. Okay, I would like us to do this. Okay, let us try to give some equivalent form for this. Okay, what if we let delta z, what if we let delta z over z be, let's say, m. Okay, so we can write in this manner, the limit of this expression, natural logarithm of 1 plus your m here. What will happen here is it would also affect your numerator, because we cannot, of course, substitute that here because we still have the exponent being undefined, making our entire expression undefined. This would mean now your delta z in this form will be changed into, or can be computed as, m times z, right? So we can substitute here. It will become 1 over m times z. And take note, we are changing the delta also as well here because we don't have any more delta z. This is actually m z at this point. Okay? Don't worry about that. We'll return to the equivalent form for that later on. Okay, so just don't worry about that one. Now, what I would like to do next here is to provide you with this specific expression. 1 plus m, you have here 1 over m to the power of 1 over z, as still mz approaching 0. Why do we have this? Okay, it's because this has specific equivalence. Okay, if we're going to apply this now using the power law as mentioned here earlier, this could be written further as the limit of your mz approaching 0. You will have your 1 over z using the power law, and you will have here the natural logarithm of 1 plus m to the power of 1 over m. This form is actually identified already as the equivalent form for, and not that one, by the way. It's actually just this item here. Just this item here. You have 1 plus m to the power of 1 over m. This is actually the definition of the Euler's number E. Substituting that, you will have the form here, the limit of still your mz approaching 0, 1 over z, and the natural logarithm of your E. Okay? Natural logarithm of E. We know that the natural logarithm of E, okay? Sorry for that. It's still mz, right? The natural logarithm of E is just equal to 1. And since mz earlier was delta z, you will have here the limit as delta z approaching 0 is 1 over z. This doesn't have any delta z in its function, so we take it as a constant. Basically, the final form here is 1 over z. This is the proof that from your function, which is the natural logarithm of z, using a definition and some properties of logarithms, and very important item, which is this, the definition of the Euler's number, E, we're able to guarantee that the derivative of the natural logarithm of z is just 1 over z. And since we have proven this already here, we might be using that in some instances later on and situations. Okay, please try to review all of the process included here together with some concepts discussed. Thank you very much for watching.